right. Today, section 6.1, again, we're doing some integration. We're going to be simplifying the integrand first today, and we're also going to look at that integration of 1 over x. So let's go ahead and start with that integration of 1 over x. If we think about 1 over x as we've done before, we would bring that x to the numerator. So we'd have the integration of x to the negative first dx. Nothing different there. If we were to increase our exponent by 1, we would end up with an x to the 0, and we would divide by that new exponent of 0 plus c. That's where our problem comes in. We can't divide by 0. That's undefined. So we need to go back and think about where we took the derivative of something to get 1 over x. And that something was the natural log of x. So we have the integration of 1 over x dx is going to equal the natural log of x plus c. Now we do need to be careful because when we take the natural log of a value, it cannot be less than 0 or equal to 0. So to show that, we're going to take and put an absolute value sign around that x. So we know that we can only take the natural log of a positive value. So we end up with the natural log of the absolute value of x plus c is the integration of 1 over x. In example 2 here, we can throw anything together at this point in time that we've done. So we have the integration of e to the x plus 1 over x dx. Integration of e to the x, remember, is e to the x plus the integration of 1 over x, we just talked about, is the natural log of the absolute value of x plus c. In example 3, I've given e to the x a coefficient, and I've multiplied the numerator of 1 over x by 3. Again, we can break these integrations up, these coefficients, and we can take and look at it as 5 times the integration of e to the x dx plus 3 times the integration of 1 over x dx minus the integration of 2 dx. We could even bring this 2 out in front of the integration symbol, so we just have 2 integrations of dx. I don't expect any of us to write it in this form, but it's just a way of showing what it's going to look like in our mind. So the integration of e to the x, we know, is e to the x, so I have 5e to the x, plus the integration of 1 over x is the natural log of the absolute value of x. So I get 3 natural logs of the absolute value of x, minus the integration of 2 gives us 2x plus c. And that's going to be our original function. It does get a little more complicated when we get a fraction with multiple terms in the numerator divided by an x. But we can again simplify this through our algebra techniques. We can divide this x into each of our terms of the numerator. So we're going to decompose this fraction into its pieces, into single terms. So we have x squared divided by x plus 3x divided by x minus 5 divided by x dx. Now we can simplify each of these terms of the integrand. And we get x squared divided by x is x plus the integration of 3x over x, which simplifies to 3, minus this 5 over x. Again, if we see it, we should say, hey, that's a natural log. If we don't, we could bring that to the top, see it as an x to the negative first, integrating x to the 0 over 0, and say, wait a minute, I know that integration. So I'm going to leave it as simply 5 over x, because I know that integration. We can go ahead and simplify this. If we integrate x, we get x squared over 2 plus the integration of 3 is 3x. The integration of negative 5 over x is minus 5 natural logs of the absolute value of x plus c. And that will give us our original function as well. In example 5, we get just a little more complicated because we can't just break up that numerator. That numerator is being squared. So before we can begin integration or decomposing our fraction, we need to multiply x minus 1 squared out. Multiplying that out, we get x squared minus 2x plus 1 divided by 2x dx. Now if we think about this 1 over 2x, remember again, there is a 1 all the way out on the outside of this, so we can think of this as a 1/2 times that integrand. So I like to bring that 1/2 all the way to the outside before I start decomposing. So I got I have 1/2 the integration of x squared minus 2x plus 1 over x dx. Decomposing this, I have 1/2 times the integration of x minus 2 plus 1 over x dx. So I've decomposed and simplified all in one term, or one step. So x squared divided by x is x, 2x divided by x is 2, and 1 over x I'm leaving because I know that integration again. Now I can go and integrate each of these terms. So I have 1/2 of the integration of x is x squared over 2. The integration of 2 is 2x. The integration of 1 over x is the natural log of the absolute value of x plus c. Again, I can put that plus c on the outside of this integration of these terms because 1/2 times c is 1/2 c, but half of a constant is still going to be a constant. We can simplify this and clean this up. We can put a common denominator inside here. So we have x squared minus 4x plus 2 natural logs of x all over 2 plus c. And I can multiply that 1/2 in with that term. And we'll see that we have x squared minus 4x plus 2 natural logs of x divided by 4 plus c. We could even take this a step farther if we remember our natural log rules. This coefficient of the natural log can, and we could see in a testing situation where that was our exponent. So we could really see this as x squared minus 4x plus the natural log of the absolute value of x squared divided by 4 plus c. And if I square the natural log of the absolute value of x squared, if I square an absolute, I'm going to get a positive number. So this would allow us to just simply write this as the natural log of x squared. I have just a couple more examples here. In example 6, just looking a little different, I can take this 1 over x, I could rewrite this as x squared plus 3x minus 9 all over x, or I could multiply that 1 over x into each of our terms. Either way, we're going to see the integration of x plus 3 minus 9 divided by x dx. The integration of x gives us x squared over 2. The integration of 3 gives us 3x. The integration of 9 over x gives us 9 natural logs of the absolute value of x plus c. Again, we could find a common denominator. We could take the coefficient and bring it up as our exponent. But at this point, we're good to get to that point. I show example 7 because it's very similar to a problem that you're going to see in your assignment. The integration of e to the x plus x to the e. So we're just going to play around with what's a variable and what's not a variable. So e, remember, is a number. X is our variable. And that tells us right here the dx. We're integrating with the variable of x. So if I integrate e to the x, the integration of e to the x again gives us e to the x. The integration of x to e, well, if I have x to a number, our rule is to add 1 to the exponent. So I have e to the x to the e plus 1. I'm going to divide by that new exponent, which is e plus 1. to then I'm going to add c. And there's our answer. And we're going to go ahead and leave it like that. We could, again, find a common denominator. This gets to be on the ugly side to do that. Happy integration.